This is the graphical examples of constructed discrete window functions and their discrete Fourier transform frequency responses. In these figures, it shows the graphical examples for rectangular window, Hamming window, Blackman window, and the last one is Kaiser window. For this example, we need to use the window method to determine the impulse response Hn for a low-pass FIR filter with the following specifications. We need to solve for n from 0 until 5. So given in this equation is the passband frequency Fp, transition with delta F, stop band attenuation AS, and sampling frequency Fs. So first, we need to check the value of stop band attenuation AS, which is equal to negative 50 dB, and refer to the window function table. So this negative 50 dB, so as we refer to the window function table, the stop band attenuation, so the window function that should be selected is the window function which has the attenuation, stop band attenuation value higher than the given stop band attenuation in this specification. In this case, the given value of stop band attenuation is equal to negative 50 dB, so we should select the window function which has a stop band attenuation AS higher than the given value. In this case, we choose Hamming window as the specified stop band attenuation. So for Hamming window, it has the transition with delta F 3.3 divided by n, and the window function Wn equal to 0.54 minus 0.46 cos 2 pi n divided by n. So the next one, we need to calculate passband cutoff frequencies, where we need to calculate based on the other parameters are normalized against the sampling frequency. So this is the sampling frequency given in the question, Fs. So to calculate the Fp, we divide the value of given Fp in the specification 1 kHz divided by the sampling frequency 5k. So normalize the values by dividing with sampling frequency and then convert to omega p. So all the values of omega must be in terms of pi function. So the next one, we calculate the transition with delta F. First, we normalize. Given in the equation, the specification, the transition width is 500. So we normalize by dividing with sampling frequency 5 kHz and then convert to delta omega. So we have this value. So the next one, we have stop band cutoff frequency that based on this equation, delta F equal to Fs minus Fp. So we rearrange this equation and we determine Fs and convert into omega s. The next one, we calculate the center or cutoff frequency, which is based on this equation, and we convert to omega c, which is equal to 2 pi fc. We have this value. And the last one, we need to calculate the constant phase delay. But first, we need to determine the window length that based on this equation and multiply with delta F equal to c. Delta F is equal to 3.3 divided by n from the Hamming window equation. So we determine the value of n and we determine the constant phase delay, which is equal to this one. So next, we can determine the value of Hn, which is equal to Hd multiplied with window function Wn for n from 0 until n. Otherwise, it will be equal for 0 outside of this region. So HDN is equal to this equation, sine omega c in bracket n minus alpha, based on the shifted to the right rule, divided by pi in bracket n minus alpha, while the window function wn is based on this equation from the Hamming window, 0.54 minus 0.46 cos 2 pi n divided by n. The next one, we calculate based on the n from 0 until 5 given in the question. So we substitute the value of n from 0 until 5 in this equation, and we have hn for each n from 0 until 5. And the last one, we write the hn in terms of this format, while the bold one is for hn n equal to 0. If the question requires to calculate the FIR filter for lower or higher values of n equal to 3 or n equal to 7, 9, 11, just substitute the n value in this part for hn.